Welcome to our presentation. The title of our paper is SeqL, Secure Scan Locking for IP Protection. The authors are myself, Seetal and Aydin from Hardware and Embedded Cyber Threat Research Lab at NC State, and Akash Kumar, Chair for Processor Design at TU Dresden. This slide describes our threat model. Outsourced fabrication is the most popular business model among the semiconductor companies today. The integrated circuit design flow consists of various steps which can be broadly classified into logic synthesis and physical synthesis steps. The outsourced fabrication model is cost effective, but the remote foundry may be untrusted, leaking sensitive design information. Alternatively, an adversary can purchase an integrated circuit from open market and reverse engineer the netlist through depackaging, delayering, and imaging. In either case, the adversary is able to obtain the gate level netlist. In order to secure the design, the designer is able to add an intermediate step of logic locking between the logic synthesis and physical synthesis steps, with the goal of enhancing security. This logic locking step adds key gates with one input driven by a secret key, and the secret is known only to the designer. There are multiple possible key gates proposed in the literature, including XOR, XNOR, multiplexer, lookup tables, and OR, to name a few. The adversary tries to decrypt this key through various techniques. The adversary uses the netlist alone or can make queries to an activated IC along with the netlist and attempt to decrypt the key. The first class of attacks are known as Oracle-less attacks, and the later types of attacks are known as Oracle-based attacks. Boolean satisfiability-based attack, or in short SAT-based attack, is the most popular attack on logic locking known to date. SAT-based attack works by converting the gate level netlist to conjunctive normal form, or in short known as CNF. CNF is a logical AND operation on Boolean clauses where each Boolean clause is an OR operation of literals in true or complemented form. There are multiple steps involved in the conversion of netlist to CNF. We can explain this with the example of a simple circuit shown in the figure, consisting of a 2-input NAND gate and whose output is encrypted with a 2-input XOR gate. The first step in the conversion involves assigning each net in the circuit with a Boolean variable. In the example, the inputs of the 2-input NAND gate are A and B, its output is D, and the 1-bit secret key is K, and XOR gate output is C. Next, each gate is converted to CNF as a function of its input and output Boolean variables. In the table shown on the top, we show how to formulate logic gates in the example as CNF. The details of how to convert each logic gate to CNF is beyond the scope of this presentation. Subsequently, the CNFs obtained for each gate inside the circuit are all logically ANDed together to create the CNF of the entire circuit. Let's call this C of X bar, K bar, Y bar, each of which are vectors of multiple bits. SAT-based attack works by creating two copies of C, which is C X bar K1 bar Y1 bar and C X bar K2 bar Y2 bar, and the algorithm proceeds. The details of the algorithm are beyond the scope of this presentation, but to explain in short, the algorithm uses the CNF along with queries to the activated IC to decrypt the key. The SAT-based attack has a formal property that upon termination, it is guaranteed to return the functionally correct key. SAT-based attack is designed for combinational IPs. However, real-world IPs are sequential in nature. It is well known that scan chains convert a sequential circuit to a combinational circuit for the purpose of testing. Scan chain is not deactivated after testing to facilitate debug of customer returns. The attacker exploits this design feature in order to launch the attack. Hence, SAT-based attack can be applied to sequential IPs in a straightforward manner by applying stimuli through primary inputs and scan chains and record the responses through primary outputs and scan chains. For an IP deeply embedded within an SoC, primary inputs and primary outputs are not accessible outside the SoC and are only available through scan chains. In such cases, both stimuli application and response recording are carried out entirely through scan chains. The figure shows such an IP deeply embedded in an SoC. All of its inputs are controlled by the register Ri and outputs observed through the register Ro. The IP itself can be sequential in nature. The entire set of flip-flops inside the IP, inside the register Ri and the register Ro, are stitched together to form a single scan chain with input Si and output So. For the sake of simplicity, we show a single scan chain. In practice, however, there are multiple scan chains and compression hardware like decompressor and compactor in an embedded deterministic test environment. In this context, the attacker uses the bypass mode to have direct access through scan chains to launch the attack. In order to prevent SAT-based attacks through scan chains, several design for security or in short DFS techniques have been proposed in the past. The first is Fortis, which enables structural tests before chip activation. However, Fortis is vulnerable to multi-cycle attack. The second one is Robust DFS, which introduces additional scan cells to drive the key gates. However, Robust DFS introduces an additional 4 to 1 multiplexer per flip-flop and necessitates the global routing of an additional test signal, making it impractical. Finally, we have the encrypt flip-flop technique, or in short EFF, which locks the output of scan flip-flops in the non-critical timing paths. Because this paradigm is verification friendly and scalable to large IPs, we focus on scan locking and its security. In order to prevent SAT-based attacks using scan chains, EFF technique performs scan locking using XOR XNOT type key gates. The figure on the left shows how scan locking is performed using the EFF technique. The designer adds XOR XNOT type key gates at the output of the scan flip-flop, and the output of the key gate is broadcasted to the combinational logic as FQ and to the input of the next scan flip-flop as SQ. EFF style scan locking was shown to be insecure by the ScanSat attack published in ASPEED Act 2019. The figure on the right has two subfigures, A and B. Subfigure A shows a sequential circuit with a single scan chain. The combinational logic is locked using two qubits, CK0 and CK1. There are 4 flip-flops, 1, 2, 3 and 4. Scan flip-flops 1 and 2 have feedback, while scan flip-flops 3 and 4 do not have feedback. In the EFF technique, there is no restriction about feedback. Hence, without loss of generality, let's assume scan flip-flops 1 and 2 are locked. All key bits CK0, CK1, SQK0 and SQK1 contribute to the functional operation in the EFF technique. Subfigure B shows the corresponding scan unrolled circuit based on ScanSat. If we launch SAT-based attack on this scan unrolled circuit, the functional portion of the decrypted key is CK0, CK1, SQK0, SQK1 is equal to 1001, which is correct. Hence, EFF is insecure. In order to secure scan chains, we propose SeqL, which locks scan flip-flops without feedback and performs functional isolation. The figure on the left shows how scan locking is performed using the SeqL technique. In SeqL, the designer splits the output of the scan flip-flop being locked into two branches, one that goes into combinational logic FQ and one that is fed into the input of the next scan flip-flop SQ. Only SQ is locked, leaving FQ unencrypted. We also add a transmission gate in the SQ path to gate off toggles in the functional mode of operation from unnecessarily switching the scan path. The figure on the right has two subfigures A and B. Subfigure A is similar to the one in the last slide except the fact that scan flip-flops 3 and 4 are locked using SeqL. Along with a key gate on the SQ output of flip-flops, SeqL also adds XOR XNOT type key gates at the input of the flip-flops to provide functional isolation. Subfigure B shows the corresponding scan unrolled circuit. In the scan mode of operation, both blue type and red type key gates appear, hence SAT-based attack is launched on this scan unrolled circuit. The red type key gates, however, do not appear in the functional mode of operation, while the blue type key gates do appear in the functional mode of operation, thereby creating functional boundary between the two as shown in the figure. Due to this functional isolation, the functional portion of the decrypted key does not contain the red type of keys and contains only CK0, CK1, FIK0 and FIK1, which are equal to 1010, which is incorrect and hence making SeqL secure. SeqL has two unique properties, functional isolation and key hiding, that makes it superior to EFF. Let's discuss functional isolation first. The top two graphs are abstract graphs of the circuit seen in the previous slide. The node C is an abstraction of the combinational logic. The red rectangles are abstractions of the key gates at the output of flip-flops. And the blue circles are abstractions of key gates at the input of flip-flops. In EFF, the blue circles don't exist, as well as the red rectangles appear both in the scan path as well as the functional path, because of which EFF is insecure. Whereas in SeqL, the red rectangles appear only in the scan path and not in the functional path, thus providing functional isolation. Below we can see the truth table for scan lock in SeqL. It consists of 4 bits, FIK0, FIK1, SQK0, SQK1, making it a total of 16 entries, but we only show 4 entries for the sake of simplicity. The second row actually shows a key which is functionally correct but scan incorrect, because of which this key is never visible to the attacker who launches the attack in the scan mode. Thus we are able to effectively hide a key from the attacker. The fourth row shows a key which is scan correct, thus visible to the attacker, but functionally incorrect, thus providing isolation and making the technique more secure over EFF. In the last two slides, we have seen the manual implementation of SeqL on a small circuit with 4 scan flip-flops. For large sequential IPs, since manual key gate insertion is not practical, it is important to automate. This slide presents the steps in the automation flow. In the paper, we have provided proof that if we lock n number of scan flip-flops, then the probability of functionally correct key decryption is 1 upon 2 power n. Due to this inverse exponential dependence, SeqL method scales to industry strength IPs. Thus, the goal is to lock as many flip-flops as possible with the goal of decreasing the probability of functionally correct key decryption, thus making the design resilient. The flow begins with the original unencrypted sequential bench, performs scan locking, scan unrolling, and then runs the SAT attack and formally verifies if the decrypted key is functionally correct. The iterative locking process continues until the design becomes resilient to SAT attack. This slide presents the algorithms we use to automatically lock sequential IPs. In the case where the combinational portion of the sequential IP is already locked, we use algorithm 1 to push some of the key gates from the combinational logic to the boundary or the flip-flops with the goal of restricting the overheads. This algorithm iteratively pushes the key gates from the combinational logic to the boundary using the flowchart in the last slide until the design becomes resilient. On the other hand, in the case where the combinational portion of the sequential IP is not already locked, we use algorithm 2 to lock the flip-flops only at the boundary. This algorithm uses a user configurable parameter gamma to iteratively lock the flip-flops at the boundary in order to make the design resilient. The user configurable parameter helps control the area overheads allowed by the designer to enhance security. This slide presents the results of SAT attack on SeqL. We show results of both EFF and SeqL with respect to locking flip-flops. As far as the combinational logic locking is concerned, we use 4 different locking schemes from the literature. The results are shown for 17 different benchmarks from MCNC and ISCAS 85 suites. The tick corresponds to being secure against SAT attack and cross corresponds to being insecure against SAT attack. The results from this table show that EFF is unable to defend SAT attack in many scenarios. In fact, if we look at DAC 12 and TOC 13 marks columns, we can see that EFF is unable to defend most of the scenarios. On the other hand, SeqL is able to successfully defend SAT attack in 100% of the scenarios across the board. This shows the efficacy of SeqL as compared to EFF in securing scan chains against SAT attack. The previous slide presented the results of SAT-based attack. This slide presents the results of post-SAT attacks, that is, more advanced attacks proposed to attack defenses against SAT-based attacks. The attacks are categorized further as Oracle-guided and Oracle-less attacks. Double dip or in short DDIP, ScanSat or in short SS, satisfiability modulo theories or in short SMT belong to the Oracle-guided category, whereas hack test or in short HT and fall belong to the Oracle-less category. All experiments were performed on the high-performance computing cluster of the university. The results are shown again for the same 17 benchmarks. Tick corresponds to being secure. Dash corresponds to greater than 1 week decryption time on the cluster. And NK corresponds to no key returned by the attack tool, indicating the hardness of the corresponding instance. In none of the cases, the key was revealed, indicating the resilience of SeqL. We have explained earlier that SeqL locks only scan flip-flops without feedback. The reason for this design choice will be explained on this slide. In the regular SAT-based attack using scan chains, if k is the scan chain length, we have k scan-in cycles and k scan-out cycles interleaved with one cycle of capture. On the other hand, the multi-cycle attack, there are n cycles of capture as shown in the timing diagram in the above figure. The below figure shows the time unrolled equivalent circuit corresponding to the multi-cycle attack. Each timestamp corresponds to one cycle of the capture in the multi-cycle attack. Since there are n capture cycles in the multi-cycle attack, there are n timestamps in the corresponding time unrolled circuit. Had we locked scan flip-flops with feedback, the corresponding key gates will appear between timestamps, making them vulnerable to SAT attack. SeqL avoids this scenario by locking scan flip-flops only without feedback. Hence, corresponding key gates appear only to the right of the functional boundary after the nth timestamp, thus preserving the functional isolation property. This makes SeqL resilient to multi-cycle attack. The previous slide explained in theory why SeqL is resilient to multi-cycle attack. This slide provides empirical results to support the same. We consider ITC circuits whose gate count is greater than 10,000 and a RISC-V core. For smaller ITC circuits, results are available in the paper. The table shows gate counts, number of scan flip-flops, and number of scan chains for each circuit considering a full scan design. The largest circuit is B19 with greater than 200,000 gates. Additionally, we show the resilience and overheads of both EFF and SeqL for all circuits. The parameter n corresponds to the number of capture cycles in the multi-cycle attack, as shown in the previous slide as well. All experiments were conducted on the high-performance cluster with an abort limit of 1 week. A tick corresponds to incorrect key decryption or being secure, a cross corresponds to a correct key decryption or being insecure, and a dash corresponds to the attack time exceeding the abort limit. Clearly, the overheads of SeqL is 1 to 2 orders of magnitude lesser than EFF. EFF fails to defend even the n equal to 1 case, considering the crosses for all the benchmarks. Hence, we do not provide results for n equal to 2 and 5. For SeqL, n equal to 1 case, it's all tick showing incorrect key decryption for all benchmarks. For n equal to 2 and 5, it's a tick for all benchmarks except B18, B19, where it has crossed the abort limit, showing the resilience. For B18, B19, we still expect incorrect key decryption if we increase the abort limit based on the theory explained in the last slide. Clearly, in all the cases, SeqL is secure, or in none of the cases, SeqL revealed the key for the multi-cycle attack, proving its resilience. This slide presents the resilience of SeqL to shift and leak attack published in ICCAD 2019. The first goal of the shift and leak attack is to find the leaky cells and shift the contents of the secure cells, in short called as the SCs, to the leaky cells. Due to the absence of secure cells in SeqL, the first goal is never achieved. The second goal of the shift and leak attack is to find a leak condition and satisfy it. Since scan chains are locked in SeqL, it is not possible to run automatic test pattern generation and find the leak condition. Hence, the second goal is also never achieved. As a result, the shift and leak attack cannot be launched on SeqL. Hence, SeqL is resilient indirectly to the shift and leak attack. Coming to overheads, SeqL has 2 extra transistors as compared to EFF due to the transmission gate that is reflected in the first column of the table, where EFF has 48 transistors and SeqL has 50 transistors. The setup time is same, 45 picoseconds. The clock to queue for SeqL is indeed smaller than EFF because the key gate is not along the functional path, rather on the scan path, making it more efficient in terms of timing. When it comes to energy per toggle in the functional mode of operation, because SeqL adds the key gate not on the functional path, and also the toggle is gated off due to the transmission gate, it is more energy efficient as compared to EFF, making it clearly superior to EFF both in terms of timing and power, but for the point that it has 2 extra transistors, making it a little less area efficient as compared to EFF. Finally, to conclude the talk, we have proposed SeqL that performs functional isolation and key hiding. The probability of correct key decryption is 1 by 2 power n, where n is the key size, making SeqL very scalable to large industry strength IPs. This is theory, and coming to empirical results, we show 100% resilience to state-of-the-art Oracle guided and Oracle-less attacks. The low overheads is very attractive, and validation on RISC-V also shows applicability to mainstream industry practice. We have source code of SeqL with us. If anybody is interested, please forward the request to me, and this is my email ID. Thanks to everyone for attending the talk.